Hi everyone, my name is Alexandra Villanueva,
And my name is Mason Munoz.
and we did our CFD project over the flow over a 2D Tesla Cybertruck.
So, CFD, or computational fluid dynamics, is the use of computers and numerical methods to solve problems involving fluid flow, heat transfer, and other things. This powerful technique spans a wide range of industrial applications such as aerodynamics of vehicles and electrical cooling of equipment. CFD analysis reduces long hours of design, prototyping, and development and testing.
All right, so first and foremost, one essential automotive development is reducing aerodynamic drag. More specifically, in electric vehicles, air resistance can heavily impact the number of miles that can be squeezed out of a battery pack. So, for instance, in the Tesla Cybertruck, for a better performance, Tesla wanted to reduce the drag, and for that being, the design only features straight lines, and the roofline gently declines down towards the rear of the truck. So our work will consist of mainly determining the flow regime over the model. We will be evaluating the coefficient of drag and lift using CFD analysis. We're doing this because Elon Musk did claim it would have a low drag coefficient via Twitter of approximately 0.3. And for our analysis, we will be considering the Tesla Cybertruck 2D model.
So, this is a Tesla Cybertruck. They're relatively uniform in 3D space, so we can use a 2D side profile to analyze it in CFD, which we made in SolidWorks. Before actually starting the analysis, we made a schematic that details the domain that will be used in Fluent. Here we have indicated the wall, inlet, outlet, and the bottom wall. And as mentioned, we have the side profile of the Cybertruck.
All right, so for our meshing, our mesh will consist of all triangular method of approximately 5-inch elements. And we want to create a very fine mesh around the Cybertruck profile. We're going to use edge sizing of approximately 1 inch. And we're also going to use refinement of a value of 3 for the enclosure just to increase the accuracy of the solution. Our main goal is to have a uniform meshing, as it can be seen on the left, whereas on the right you can see some inconsistencies, and those inconsistencies can cause inaccuracies in your solution.
Our final mesh was constructed in Design Modeler. At the front, you can see we have 2 Cybertruck lengths, and at the back, we have 5 Cybertruck lengths. At the top, we have at least 1 additional Cybertruck height in order to correctly display all of the contours that we need. As mentioned before, we used sizing and refinement to further decrease the size of the cells around the Cybertruck in order to increase the accuracy of the simulation. As we zoom in here, we can see the very fine cells around the Cybertruck that will be used as areas of interest in the calculation. For our setup, we used a pressure-based transient state, assuming turbulent flow carried out using the K-epsilon model. We used a realizable model for this because it generally tends to perform slightly better for a wider range of flows. And also we used an enhanced wall treatment to increase accuracy. So for our material, we assumed air as if we're simulating a virtual wind tunnel. For boundary conditions, we assumed a velocity at the inlet set to 60 miles per hour or 26.8224 meters per second or 88 feet per second. Our outlet was set to a pressure outlet with a gauge pressure of 0 pascals. Our solution method was the second order upwind, and for our transient formulation, we used a bounded second order implicit. All of our monitors were set to 1 times 10 to the negative 6, and we wanted to make sure that we used a small enough time step in order to reach convergence within the number of iterations per time step.
So here we have our velocity contour animation. As you can see, the flow goes over the 2D profile uniformly, and no separation occurs until it hits the rear end of the vehicle, where vortex shedding occurs. From this, you can see that the Tesla Cybertruck is indeed aerodynamic. Here you can see the pressure contour animation. From the animation, you can obtain that the pressure is pretty uniform throughout the top end of the 2D profile, which seems to be a goal in designing the Cybertruck. However, a peak point can be viewed at the top end of the vehicle and plays a critical role in why the vehicle is pretty aerodynamic. At the end of the vehicle, you can see the pressure changing quickly due to the separation of flow and the formation of vortex shedding. So after the simulation, we went back and retrieved the coefficient of drag plot, which seems to be pretty uniform throughout. However, we computed the drag coefficient where we obtained a value of 0.447, which is pretty close to the assumed value of 0.3. Moreover, the results were a bit off, also due to the analysis being 2D, whereas if it was 3D, it would give more accurate or realistic results. The lift coefficient was as well retrieved at a value of 5.344, where a higher lift coefficient means a smaller effective weight of the vehicle, which decreases energy consumption.
That's it for our video. Thank you for watching. We hope you learned something new.